Bioinformatics Micromodules, the forward and backward algorithms. In this module, we introduce two algorithms that solve the first problem related to hidden Markov models. Both algorithms use dynamic programming to avoid explicit enumeration of an exponential number of possible state sequences. Let us first recap the definition of the problem. Given a fully specified hidden Markov model, which means we are given the values of all the initial, transition, and emission probabilities, we want to compute the probability of an observation sequence. Mathematically, we can state the problem as computing probability of O given theta, where O is the observation sequence and theta is the model parameters. As mentioned before, the main difficulty of this problem is that we do not know the actual state sequence that produced the observations, and therefore we should consider all the possible state sequences. In other words, as shown here, we want to turn probability of O given theta into the product of probability of O given Q and theta and probability of Q given theta, and sum over all possible Q, which has an exponential number of possibilities with respect to the number of observations. Conceptually, after this decomposition, the first probability term, probability of O given Q and theta, can be easily computed as a product of emission probabilities, while the second term, probability of Q given theta, can be easily computed as a product of initial and transition probabilities. The main challenge here is then how we can compute this sum without explicitly enumerating the exponential number of possible state sequences. We do that by dynamic programming. The first dynamic programming algorithm that we will discuss is the forward algorithm. Recall that in dynamic programming, the first thing we need to do is to define the subproblems and decide how the results are stored. In the case of the forward algorithm, we define this table alpha that stores the results of the subproblems. Alpha has two dimensions, namely a dimension of steps and a dimension of states, indexed by variables t and I respectively. The table entry alpha ti is defined as the joint probability of the first t observations, and that the state in step t is Si, given the model parameters. Each of these entries corresponds to a subproblem. So why is it a good idea to define the subproblems in this way? First, as explained earlier, in order to compute probability of O given theta, one way is to sum over probability of O and Q given theta of different Q, because each of these terms can be decomposed into two terms that can be computed easily. Second, in dynamic programming, we always want to solve easier subproblems first, the results of which will then be used to solve harder subproblems, and ultimately the original problem. In our current case, instead of considering all observations at the same time, it is better to consider only the first t of them, which should be easier. Finally, to avoid considering the exponential number of possible state sequences, we only consider the state in one step at a time, and so we fix the state of only step t in the definition of the subproblems. Now that we have defined the dynamic programming table, as in all dynamic programming algorithms, next we need three things, which are 1. A way to initialize the table, 2. A recursive formula for computing a table entry based on some other table entries, and 3. A way to get the final result from the table. For the initialization, since the subproblems become easier and easier as t becomes smaller and smaller, it is natural to consider the boundary case of t equals 1. According to the definition of the dynamic programming table alpha 1i is equal to probability of O1 and Q1 being Si given theta, which can be decomposed to the product of the initial probability of state I and the emission probability of the first observation by state I. These two values are both given as part of the model parameters theta, and thus we can directly compute the entries for t equals 1. Next, we need a recursive formula that computes each entry in step t based on the entries in step t-1. The recursive formula is shown here. Intuitively, you can consider it as transiting from state j in step t-1 to state I in step t, followed by emitting the observation in step t. Therefore, we have alpha t-1j multiplied by the transition probability pji and the emission probability ei bracket ot. And we sum over all possible states j of step t-1. While this intuitive understanding is good for memorizing this formula, it is not a formal proof. We will show a formal proof of this recursive formula later. Finally, after computing all the entries in the table, we need to get the answer to our original problem, which is the value of probability of O given theta. We can do it by considering the joint probability of O and the state in the last step, which is step M, and sum over all the possible states in this step. If you check the probability term carefully, you would notice that it simply means summing all the entries in the table that correspond to step M. With all three sets of formulas ready, we can now use the forward algorithm to solve the data likelihood problem. However, before we do that using an illustrative example, some of you might be interested in seeing a formal proof of the recursive formula. And here you are. At the beginning of this page, we see the definition of the table entry alpha ti, and at the end, after some derivation steps, we get the recursive formula that involves entries in the previous step, namely alpha t-1j. We're not going to go through this proof, but basically, you only need the three basic probability rules that we introduced before in order to do this proof. You're encouraged to try it by yourself to see if you can also derive the recursive formula. Now, let's see an example of using the forward algorithm. Assume that we have the hidden Markov model shown, and a run of it has produced the observation sequence tail, head, tail. We want to compute the likelihood of this observation sequence. As a reminder, here we show the definition of the dynamic programming table alpha, the initialization formula, the recursive formula, and the formula for computing the final result. Using these formulas, we can compute the values of the table entries, where each step is shown as a row and each state is shown as a column. The two entries in row 1 are computed first using the initialization formula. Then the two entries in row 2 can be computed by plugging in the values of the entries in row 1 into the recursive formula. Row 3 can then be computed in the same way. Finally, summing the two entries in row 3, we get the overall answer, which is the probability of observing tail, head, tail, given the model parameters. It is important to analyze the time and space complexity of the forward algorithm to make sure that it is efficient. To do that, we first notice that the dynamic programming table has n times m entries, where n is the number of possible states and m is the number of observations. To compute each entry in the table, we need to sum up n terms that correspond to the n possible states, and each of these terms can be obtained by a constant number of multiplications. Therefore, the time needed to compute each table entry is order n, and thus the whole forward algorithm requires order n squared m time. If we take the number of states as a predefined constant, the algorithm has a linear time complexity with respect to the length of the input, which is the observation sequence. As for space complexity, since we fill the table row by row, And once a row is filled, all previous rows will not be needed anymore. We only need to keep 2 rows at any time. Therefore, the space complexity of the whole algorithm is order n, which can be considered constant space when the number of possible states is fixed. In summary, the forward algorithm allows us to compute the data likelihood in linear time, which would otherwise require exponential time if we sum over all possible state sequences in a brute force manner. The forward algorithm is intuitive because each subproblem involves a number of first observations. However, it is not the only way that can compute the data likelihood efficiently. We now describe another algorithm called the backward algorithm, which is also a dynamic programming algorithm with the same time and space complexity as the forward algorithm, but it works backward instead of forward. To do that, we define a new dynamic programming table, beta, in which each entry corresponds to a subproblem. The entry beta Ti is the probability of the observations from step t plus 1 to the last step, given that the state in step t is Si in the model parameters. Therefore, instead of making the problem easier by considering only the first observations, here we make the problem easier by considering only the last observations. Notice that although as in the forward algorithm, we want to fix the state of one step, in the backward algorithm, we put the state variable Qt to the condition part rather than as a joint probability with O. Intuitively, this is related to the Markov property that once the state of state t is given, the observations in subsequent steps become independent of all the previous states. Now, with the dynamic programming table defined, we again need the initialization formula, recursive formula, and a way to get the final answer from the table. Since the backward algorithm works from the last step backward, we initialize the table by computing the entries for step m-1. The resulting initialization formula is shown, the proof of which will be given later. Next, we have the recursive formula that computes an entry in step t based on the entries in step t plus 1. We will also show the proof later, but intuitively, it is like considering all possible transitions from step t to step t plus 1, followed by an emission of the observation in step t plus 1. Finally, once we have the entries for step 1, we can use this formula to compute the overall data likelihood. This formula is not difficult to verify, and you are encouraged to do that by yourself. One special remark here is that instead of initializing the table by filling in the entries in t equals -1 using the initialization formula, it is common to instead initialize the table by setting the values of all entries in step m to 1. According to the definition of the beta table, we should not really have a row for t equals m, since we do not actually have observations m plus 1, and thus the entries in row m are not defined. However, you can verify that by filling the constant value of 1 to this extra row, we can compute all other entries of the whole table using the recursive formula alone without the need for the initialization formula at all. You can choose to initialize the beta table in either of these two ways. Now, for those of you interested in the derivation of the initialization and recursive formulas, you're encouraged to try it on your own, and you only need to use the 3 basic probability rules that we introduced before. You can look for hints from what we are showing here in case you get stuck at a certain point. Finally, let's see an example of using the backward algorithm. The hidden Markov model and the observation sequence are the same as the ones we used in the example for demonstrating the forward algorithm. As a reminder, we show the definition of the dynamic programming table, the initialization formula, the recursive formula, and the formula for getting the final answer from the table. The completed table is shown here. Since there are 3 observations in the observation sequence, as mentioned, we can either have an artificial row 3 initialized with the constant value of 1, or use the initialization formula to fill in the values in row 2 directly. In either case, we fill in the entries of row 2 first, and then those in row 1, and finally, based on the entries in row 1, we can compute the overall data likelihood. If you compare this value with the one we got using the forward algorithm, you will find them exactly the same as expected. In the next module, we'll move on to discuss the other problems related to hidden Markov models.